Okay, if you can, just type a quick yes in the chat. Wonderful, thank you. So this morning we're going to be discussing drainage deficiency and how we evaluate that and different ways of remediation depending upon um, what the issue is and our approach as engineers to deciding or determining what the source of the problem is and the best way to approach fixing it. So just a little bit about myself. I've been with Kipcon for a little while. My background is, I'm a licensed civil engineer, but my background is in site work. So largely I work on anything but the building. I know quite a bit about buildings as well, but my expertise is in site work, in things that are in the ground or above the ground. And a lot of times the projects that I deal with have to do with stormwater management, whether that is deficiency or design of new facilities. Here's the outline for our topics today. So we're going to look at just some types of deficiencies that look very similar, but oftentimes have different sources. And I'll talk a little bit about what I looked at for each one. There is no formulaic approach to evaluating drainage deficiencies, but there are certain things that you tend to look for over and over again, and it becomes a process of elimination. So we'll look at that. We'll talk about just some stormwater management basics, uh, how the hydrologic cycle, what happens to water, how it sits on the surface, and how it sits in the ground. We're going to review quickly the engineering approach to drainage remediation and what we do as engineers and how we approach it. Then we're going to look at some case studies. We'll look at 3 different case studies where we're going to wrap up with a stormwater basin, which is the bulk of the complaints that I get from clients for things that are obviously not functioning. So we'll look at some management points for that as well. So as I mentioned, drainage problems can occur for a variety of reasons. And when we are evaluating it, we can't just look at it and say, well, there's standing water or there's erosion or there's this or that. So here's what you do. So we have to look at what's going on around each of these problems to see what the source is and what the best solution is. Because even if the sources are similar, the solutions might be different. Oftentimes, short-term repairs, such as trying to put stone on standing water, trying to divert water to a different place, just as a temporary measure does not last. So whenever you're evaluating drainage deficiencies, you want to look for a longer term solution it's going to be more cost effective. It's going to last longer. It's going to accomplish the goal that you're setting out to do. So let's jump right in. So standing water is a very common complaint, and it can happen for a variety of reasons. Here are 2 examples here. So we have in the top left picture some storm damage. So we've got some standing water in a swale. You could see it runs very, very close to the homes, through really right through the center of this HOA. There was a very large storm that did a lot of damage, pumped a lot of silt into the surface stormwater system, the swale system, in through the piping, and it resulted in a standing water condition. The lower right-hand side, we see this very, very often in communities that have older pavements that have either settled over time or there's patchwork, and the water just isn't getting to where it's intended to go anymore. This particular community, there's a catch basin. I don't know if you could see it, it's off in the distance there, but the water is intended to flow to that catch basin, but because over time these areas have settled from just vehicles standing on the pavement and from um, some patches that are in some other areas of this parking area, this water is trapped. Essentially, it's just sitting there. So I want to contrast that with some standing water, and I'm sorry I don't have a picture of the basin, but there was some standing water along the around the outlet structure in the basin. And when I looked on the other side of the berm from the outlet structure, I saw what is in the upper left-hand corner here. So, and this is a wetland area. So the basin discharges to this wetland area, which during the spring, as you know, it rains a lot in the spring. We've got a high groundwater table.
Oh, like I'm seeing.
There was nowhere for that water to go, so it was backing up into the basin.
From the what group?
Somebody's microphone is on. Could you kindly mute? Thank you. So in the bottom right-hand corner is the wetland mapping, the New Jersey
Oh,
wetland.
no, we're good. We're good. No, we're in the process of finding something with.
Chelsea or Jen, are you able to global mute
Thanks.
everyone? Thank you. So at the bottom right-hand corner is
It comes furnished.
Paul Langer Massini.
And
Paul Langer
yeah, we have a
Massini.
vendor for that as well. So I appreciate the call out. Okay. Bye.
Paul Langer Massini, can you kindly mute your microphone? I'm not sure if he has me muted. So getting on with it, here's the wetlands mapping. The area in light blue is actually delineated wetlands. So contrasting with our previous slide, we've got standing water that is in a developed area. It's either because of storm damage or just deterioration over time. We can do something about these problems. We can mitigate these problems in a way that's going to eliminate that standing water. Whereas here we have a condition where we're subject to the forces of nature. We cannot change the standing water conditions in this wetland area. All we can do is deal with it. So in this particular case, and again, I'm sorry I don't have pictures of this basin, but what we were able to do was do some uh, measures in the basin that sort of mask the water. We can't eliminate this, couldn't eliminate the standing water because we can't manipulate the wetlands and we can't raise the basin. So we had to do some things to deal with the standing water. Seepage. So here are two examples of two different sites that have seepage, water just bubbling up, if you will, out of the ground in different areas. And the causes of the seepage are from two different conditions. So the top picture here, this is a brand new construction, and it's adjacent to one of the types of wetland areas that I just showed you. So this is in the spring, the groundwater table is very high, and the water is taking the path of least resistance to the surface. So we were able to put in some subsurface perforated piping for this particular community and pipe it into a catch basin. That water is always going to want to try to bubble up to the surface, but we were able to intercept it with some piping beneath the ground that will give it a void area to run to and pipe it off to the stormwater system. And it was successful. We were able to dry up the ground. The bottom community here, you would think it would be a similar situation. You see the stormwater basin there. Where I'm taking this picture from, and back of me is actually a wetland area. So it would be easy to think that this was a groundwater condition. But there were some other factors involved here that caused us to have the utility take a look at some of their subsurface utility piping. And as it turned out, there was actually a leak in one of the utilities. There was a damaged pipe, and it was causing water to come up to the surface here and bubble up through the cracks in the pavement. So in repairing those subsurface utilities, they were able to eliminate this seepage condition in the pavement. Erosion. So erosion is when the turbulence of water flowing over the surface of the ground takes the soil with it. And so you'll start to see erosion develop, like in the top picture here. This is actually a little swale where the water concentrates. When it rains, the water flows down to this area that carries the water to the basin. I'm actually standing in the basin taking a picture of this erosion. You could see where it's carried the soil with it. This is actually very sandy soil with topsoil on top of it down in South Jersey, so they could get grass to grow very difficult time getting grass to grow. And as a result, there was this channel was not very stable when the water flowed through it. So it took the topsoil with it, exposed the sand, and every time it rained, it continued to carry more and more soil with it, eroding it. This bottom picture here is the outflow from a basin out in Pennsylvania, the Westchester area in Pennsylvania. This is actually storm damage. So instead of over time just carrying away
We
topsoil,
don't see any picture, sorry. It is, yeah.
can everyone see my screen
No,
for the webinar? No?
we're seeing an Associa advertisement.
It's your
We're seeing
desktop.
somebody's
also.
screensaver or desktop or whatever you call it.
I think somebody's on another meeting and shared their screen. I'm gonna I tell you what, I am going to try to reshare my screen.
Somebody
How about
named
now?
Madeline Tarversi screen is what's showing.
Is whoever has their screen share on, could you kindly turn off your screen share? Are you able to see my webinar again?
No, it's like I said, a woman named Marilyn Tarves screen is what we're seeing.
Okay, Marilyn Tarvis, can you hear me?
the screen, click on N Rebel's screen, and you'll get back to the screen that she's sharing.
Now I see on the very top, yeah, I clicked on your name. I came back to your screen.
Okay, all right.
I just clicked on your name and I'm not getting to that. I'm getting to the, oh, now it's
Okay.
changing.
Everyone
Yay.
to see
Okay,
my
all right,
screen.
great. Thank you, whoever turned off their screen share. Appreciate it. Just a reminder, please kindly mute your microphone and don't screen share unless you're on another Zoom meeting. Thank you. So getting on with it. So this in the bottom right hand here, we have storm damage. So this is not a chipping away at the topsoil, if you will, over time. It was a very large storm that came through and blew out the outlet protection at the below the basin. You see that hill there with the fence. On the other side of that is actually the basin. So one of the things I want to point out here is that when sites are designed, they're designed for a certain storm frequency, meaning that I guess in layman's terms, a certain intensity of storm. Each one of the structures can handle a certain type of storm up to a point. There are times, as we know, we've seen some very large storms in the past decade or so, where all bets are off. The amount of rain coming down, the intensity of that rain exceeds what can reasonably be designed, and you end up with damage. So that's why maintenance is very important. So after large storms in your communities, it's good to take a walk around and just take a look at the swales. Take a look at areas where water is concentrated and flows through, and just check it for damage, because large storms can do a lot of damage. And if you leave that damage there, it will continue to erode, it'll continue to deteriorate, and it becomes much more expensive the more you defer that maintenance. Here again is turf damage. We have on the top here. This was a fairly new construction, and because the topsoil was being washed away, we have these kind of patchy areas of grass. I'll tell you, I do a lot of transition studies, and I will tell you, pet damage is an issue. Even if a turf is installed properly and is growing quite well, pet waste creates kind of like a little fertilized area that results in these very rich clumps of grass, and then everything around it dies, and you end up with this sort of sparse grass looking type of deficiency. So I'm sure it's obvious at first when you'll see this often between like the curb and the sidewalk, where there's turf wars going on between dogs, and the turf ends up getting very burnt out, and you end up with this erosion condition. So either from water running over it or from pet damage, you can end up with an erosion condition. Flooding. This is actually a very interesting phenomenon. Flash flooding in developed areas is quite common. Again, when your communities are designed, the catch basins, the piping, the stormwater basins, they're designed to handle a certain intensity of storm. So they can handle quite a bit of water, but every once in a while we'll get these sort of cloudbursts where we get just torrential rain. It doesn't last long, but there's so much water that it overwhelms the stormwater system. So on the top left corner here, you see a picture of flash flooding in this community, and it's again down in South Jersey. It's a very flat site, so you don't have a lot of water movement when you get a lot of rain that falls at once. And it actually overwhelmed it couldn't get into the grates and the catch basins fast enough. And then the pipe pitches were very, very shallow because the site is so flat. So they got an enormous storm. This standing water will dissipate. When any flash flood, it'll start to dissipate in a very quick period of time. Usually within an hour or two, you'll go back outside. There's no water. It's like it never happened. But because the capacity of the system gets overwhelmed, that water backs up, and it looks like it's a major flood. It's a flash flood. Whereas contrasted to a major flood, whenever there's a major flood, it's because regionally, not just in a small development area, but regionally, there is an intense amount of water, a large amount of water. It's usually during storms of large duration. As you know, I'm sure anybody on this webinar today has experienced the storms we have gotten in the past 10, 20 years that are, and really over time, historically, every once in a while, you'll get a storm that overwhelms everything. The runoff goes to the rivers, the river banks overflow. There's nowhere for the water to go, so you'll get this regional flooding. So again, flooding for two very different reasons. Flash flooding, there's usually not a whole lot you can do for flash flooding. And obviously for large floods, there's not a whole lot you can do, but for flash flooding, just putting in more catch basins or trying to get the water to run faster doesn't typically work. Once that system gets overwhelmed, it's really hard to mitigate that. So poorly functioning stormwater basins. So here's two basins here. We've got standing water in both of them. And the one on the top left was severely silted. This system was not maintained. It was not cleared of silt, and the pipes in the community, everything were filled with this very, very fine muddy silt. And this, you could see where the outlet structure is, and the top picture, this was just buried in silt. So to try to cover the standing water, they filled the basin with river stone, as you can see. And this basin was largely meant to allow infiltration into the soil, and also anything that overflowed was to go out of this outlet structure here. But because it was so silted, the water couldn't seep into the ground. So we ended up excavating everything down to the sand layer and doing some improvements, and it started and jetting out all the pipes in the community, getting all that silt out of them and cleaning everything out. Now it's functioning very well. It looks very nice. The infiltration basin at the bottom here, there is no outlet structure. This is down in South Jersey where there's very, very sandy soil. This is meant, all the water is meant to flow into this and 5 other basins on the site and just sink into the ground within a period of 72 hours. This particular basin would not drain at all. They could not get this basin to drain. So we did some investigation. We did a test pit. We found that there was actually a layer underneath the very nice porous sand that was keeping the basin from draining. So again, we have two different very different causes here. On the top one, we have a maintenance issue. On the bottom one, we have a concealed soil layer that is preventing this basin from draining. two different solutions as well. So let's talk little bit about open voids and subsidence. So we get a lot of requests for investigation of what are the blanket term used across the board is sinkholes. I refer to them as open void and subsidence, and we'll see why. So this particular community here, there's an example of, and you will often see this next to a catch basin, especially in older communities, a hole start to open up next to the structure. So what this indicates to me is there's probably a bad pipe connection, or there is a lack of maintenance of the basin box itself. If you take this grate off, it actually in this particular community there's a basin box. It's precast, so there's no block or anything. It's all one piece. But sitting above that was there's what's called a riser course, and it's usually built of brick that's mortared in just to get the grate at the right levels to work with the grading. And so this was not maintained. The mortar had actually deteriorated and fallen in, and it was sucking soil in through the holes in the brick and formed this void. The one on the right is actually there's a hole right through the asphalt pavement. This particular one, I believe, if I remember the site correctly, is a bad pipe connection. The pipes, when they come into the catch basin box, they're grouted so that they prevent water from seeping in or protect against water from seeping in. If that goes bad, and if that's not maintained properly, it can start to deteriorate. Water comes in, it starts to pool the soil with it and form this void. So again, these are conditions where it's in a developed area. There's something that you can do to fix it so that it stops happening and that it's safe again, as opposed to a force of nature. So here's an example of an actual sinkhole. When I think about being out at this site, this is actually in the bottom of a detention basin out in Pennsylvania, and an infiltration basin actually. No, I'm sorry, a detention basin. There's no infiltration here. It was actually, there was a liner in this basin. There's not supposed to be any infiltration because of the limestone bedrock underneath. And they had this sinkhole that formed. They filled it in. It formed again. They filled it again. And then the sinkhole formed again. So they had a geologic engineer come in and do some mitigation here, capping this sinkhole, digging it out, capping the sinkhole, and repairing the liner, and then repairing the bottom of the basin so it didn't happen again. So whenever a sinkhole forms because of the underlying geology, there's usually an underlying geology that once, if water touches it, it will begin to dissolve, and you get these voids that start to form in the bedrock, and when they collapse, it takes everything. It takes the surface soil with it. So again, the difference between here we have these open voids and subsidence that are forming because something in the infrastructure has gone wrong, versus a sinkhole that's forming because of a natural phenomenon. So before we get into the engineering approach to evaluating drainage deficiency, I just want to go through some basics. It's very, very basic, but I think it'll illustrate for our case studies what could potentially be going on. So very simple. It rains. A lot of the rain turns into surface runoff and runs to a collection area, whether it's a catch basin, a stormwater basin, a stream, a river. The surface runoff rolls off and it joins the surface water somewhere. Some of that rain will seep into the soil. Two things can happen. It can stay in the upper layers where it evaporates or is taken up by plants and then evaporates through transpiration of the plants, or it can infiltrate deeper into the soil and go down into the groundwater table. as recharge. So every time it rains, depending upon the soil you have on a site, there's a certain amount of it that becomes evaporation again, goes back into the atmosphere. There's a certain amount of it that is turned back into recharge. Many of your communities may have recharge BMPs where before it's developed, there's a certain amount of recharge. There's a calculation that's done by the designer of the site to determine what the recharge requirement is, and the state agencies will require that recharge amount be preserved. So you may have some underground either infiltration basins or underground BMPs, best management practices, that are structures that are meant to capture that runoff. Because when you develop a site, you are creating impervious surface where that recharge cannot happen. So the designer will create structures or create BMPs that will capture that water and allow that recharge to happen. So let's talk a little bit about the difference between surface and groundwater. So again, surface water can run off when it rains to an open body of water, but also groundwater. And we saw this earlier in the pictures with the wetlands. So what we're seeing actually is when that groundwater table, that recharge zone, when that water table becomes higher, it can actually the top of that groundwater surface can be higher than the ground surface. And then what you get is standing water in wetlands or ponds, rivers, things of that nature. So anytime you're looking at a body of water that's sitting on the surface, there's the groundwater table is probably at that level or very close to that level. So when we're evaluating deficiencies, and this is just a very small, what I'm going to talk about here is we look at all kinds of things. We look at, again, as I mentioned, we look at all the conditions that are surrounding a deficiency. We try to, by process of elimination, determine what the source is. But there are certain drainage criteria that we always keep in mind when we are evaluating deficiencies. So when it rains, the water is allowed to be on the surface of the ground in developed areas or in stormwater systems for a certain period of time. So for open areas, it is 24 hours. So when it's raining, you don't want to look when it's raining and look at puddles or ponds and say that's a deficiency. You have to allow that drain down time to occur to identify the deficiency. So when there are swales, we saw in the beginning picture there where there was standing water in the swale, those swales should drain within 48 hours after the end of a rain event. I want to stress that after the end of a rain event, it has 48 hours to drain. And for stormwater basins, it's generally 72 hours. That means whether you have an infiltration basin, whether you have a detention basin or an underground basin, that water needs to drain within 72 hours. So when we're making an evaluation, there are certain conditions where we want to wait for when the ground isn't frozen, when the temperatures aren't freezing, because we can end up with a wrong evaluation. So whenever there is snow piled up, whenever the ground is frozen, when there's ice formulation, we don't want to try to evaluate it then, because we're not seeing how the system is actually intended to function with a clear flow path or with infiltration into the ground. So we want to, when we're evaluating stormwater drainage, we want to look at it typically between mid-April to like right before Thanksgiving, mid-November, because the temperatures start to change. We start to get these conditions where the ground freezes or it's snowy. So we want consistently warm temperatures for that evaluation. Also, we want to take into account, as I mentioned, whether there has been a large storm event. Because there is damage from a storm event, or because there is standing water within those drain down times that I mentioned, after the end of a storm event, it doesn't necessarily mean that the construction is deficient. It just might mean that the storm was so big that it caused the damage, or is causing the prolonged standing water. So you want to pay attention when you're evaluating, or we do, what the intensity, what were the conditions before the deficiency occurred? What were the storm conditions before it occurred? So when we're approaching engineering, when we're taking the engineering approach, we have a sort of a set way of approaching it, if you will. There are deviations, but this is the general way that we approach it. So we begin with a visual evaluation. We don't jump right into testing. We take a look at it first. We try to assess visually what those surrounding conditions are. However, to evaluate it properly, we may need to do some testing. Once we know what's going on, we can recommend a course of repair, prepare specifications to do the work. So having the visual evaluation done first, again, you might not need testing. Sometimes you may. We can't rule out that possibility, but sometimes the problem can be quite obvious. So we want to do that visual evaluation. We want to do that testing because there may be more than one way to repair it properly. Again, I don't want to talk about the difference between putting a Band-Aid on it and doing a proper repair. There may be more than one way to repair properly, and we may need to look at what those recommendations are. One may be cost effective, one not. One might be more impactful to something we don't want to impact than another. So we want to look at those alternative approaches. And again, when the visual approach is not sufficient to provide a recommendation or a cost-effective plan, we may want to do testing. This might include things like pit testing, soil borings, things of that nature, where we need to take a deeper look into what's going on. Once we understand the parameters, what the cause of the problem is, and we narrow in on a recommendation for repair, we can prepare specifications. So I won't touch on this too much here. We have a separate webinar that talks about preparing specifications in the bidding process and how that works. So I won't go into that too much here, but I will say that having specifications prepared for bidding allows contractors to all bid on the same scope of work. Oftentimes, if you go out to a contractor and without specifications and you ask them to give you a price to fix something, you will get different scopes of work. You'll get different pricing. It's hard to compare pricing and hard to make contractor selection when you're not comparing things from the same basis. So preparing specifications will give you that consistent basis to compare the scope of work and the costs that you're getting, the quotes you're getting. So let's take a look at some case studies. The first one, we're going to look at two basements that have what looks like similar problems. We're going to look at the construction process for an improvement project, and we're going to look at a stormwater in the end, so I can talk about maintenance. Maintenance is very important. I can't stress that enough. So let's look at the basement again. Similar problems, different sources, different solutions. So basement A had both of these particular communities, we got a call that there is infiltration into a subgrade basement. Can we come and take a look at it and evaluate it? So basement A, we always start, we look at the exterior first, and then we go and we look at the interior to see what's going on. So basement A, we looked at the exterior. There's really nothing that we saw that would indicate that there's something happening at the exterior that's forcing water into the interior. The ground was graded very nicely away from the exterior foundation. There were window wells, there were windows in the basement, but there were window wells there that had drainage in them. We didn't find a problem with the drains or the pipes that were in the window wells. The roof drainage, the downspouts, which they're often a culprit in basement infiltration into the foundation in the basement. But in this particular case, the roof drainage was connected very nicely, very successfully to some underground drains that led into the stormwater system. So again, basement A, nothing at the exterior that would make us think there was a problem here. Here's basement A at the interior. Here's those windows. We're looking at the areas where the opening to the windows are. We're looking for evidence of infiltration, water staining, cracks in the block, anything like that. As you can see, these look great. There's really nothing wrong with these window openings. So we can see that there's no water coming in really at the top of the foundation or through the window openings. At the bottom here, we do see that this was an unfinished basement. There is a French drain that runs around the perimeter of the basement slab. We can see here, you can see where there is evidence of water staining. You can see where there were holes, actual holes drilled into the bottom of the foundation wall here to alleviate the hydrostatic pressure. They were having water coming through the bottom of the wall. They said when they drilled these holes, the water actually projected out over top of the French drain onto the floor because of the hydrostatic pressure behind the wall. So let's switch to basement B. So that was basement A. Basement B, again, same complaint. There's water coming in at the foundation wall. So we looked at the exterior first. At first glance, we said, well, it doesn't look like there's any issue with the roof drainage. It has been diverted. We don't see where there are any areas where the turf areas are back pitched against the foundation. And at first glance, it didn't look like there was an issue. As you can see, we went down into the basement, and I don't know if you could see my cursor, but this corner here at the exterior is this corner here at the interior. So and if you can't see my cursor, it's where the white siding is on the house. That exterior corner is that interior corner in the basement. So we went down in the basement. You can see there is in that corner. It was isolated to that corner and along the floor, the water staining, and you could see where it cascades in at that top corner there and migrates down. I will tell you let me see if I have it in. I don't have other pictures of it in here, but as we went in further into the basement where that basement wall was exposed, you could see where the water was migrating along the floor from this corner. So clearly it's coming in at that corner. So we went back outside and we took a closer look at what was going on. And at the where the garage concrete apron met the driveway, there was actually a depression there, and there was you could see where the pavement had shrunk, and there was a crack that had opened up over time, and the water there was, when it would rain, the water would flow to that little low point along the seam between the garage apron and the driveway, and it was infiltrating in there, and it was taking the path of least resistance. Water will always take the path of least resistance, and got into that corner, and that's where it was coming into the basement at that basement corner. So we were able to put in a trench drain there to intercept that water and move it elsewhere so that it didn't so that the path of least resistance was into that trench drain and into the stormwater system instead of into their basement. So basement A, we determined that the infiltration was a result of the seasonal groundwater table. Whenever that water table was high, it would create hydrostatic pressure behind that concrete foundation. I'm sorry, the masonry block foundation, and force its way into the basement. Basement B was not a groundwater problem. It was a surface water problem at the exterior. So again, two different types of solutions for two very similar looking problems. So case study 2 I mentioned earlier was a non-functioning swale. When we went through the community, this swale, and the pipes had siltation and damage from a storm. So we came up with a plan of remediation. We had to, they wanted some additional stormwater infrastructure added in. So we didn't just repair what was there. We did some also some drainage improvements in this community that added inlets and really tried to take what was flowing over the surface of the ground and moving it underground, so that it was in some areas of this community, the water was becoming a nuisance in the rear of the home. So we were able to take that water off the surface, get it underground, get it into the stormwater system, so that they didn't have these problems in the future. So just to give you some visual examples of what one of these types of projects looks like, they're very, very messy at times, often very messy whenever you're digging in the ground. But in this particular case, they trenched out. You could see the new pipe lying alongside. We used concrete pipe in this case because the ground, there was a lot of movement in the ground. There was a concern that if we used plastic pipe, that we would end up with bellies in the pipe. This is a very shallow pitched community. It's very low lying. So we wanted to use pipe that was not going to flex at all and create bellies and standing water in the system. So here they are. This is a new catch basin going in. Again, you could see how very shallow this is. And again, the catch basin box is precast so that the community did not have to deal with having to maintain the box in these very wet clay soils. Here they are putting the bedding down for the pipe. You could see they're starting in the background of this trench. They're starting to line up and lay the pipe between the new catch basins. Here's the rough grading of the completed installation of the new pipe, where they're grading the surface of the ground so that the water will flow properly to where it needs to go. Here they are, they're fine grading and seeding the final product here. Here's the new flared end section. You could see the stone here at the bottom. This is called conduit outlet protection. Again, keeping in mind that erosion happens when concentrated water is flowing over the ground surface, and the turbulence of that water will tear up the ground and the soil. So at any time you have water that daylights out of a system, you want to have some sort of conduit outlet protection to dissipate that velocity and that turbulence in the water so that it doesn't do damage. And here's the finished product here. You can see very clearly how the ground slopes to get the water into the swale and moving along. And lastly, we'll look at a stormwater basin. So this particular community, they've got a couple of things going on here. We got a call because the water in Basin 1, which you see at the bottom right of the screen, this is an aerial view of this particular community, that the water was rising quite high in this basin during large storms. And you could see how close this basin is to the homes. So as you can imagine, they were quite nervous that the water in this basin was rising to such a level. Basin 1, when we took a look at it, they didn't have plans for the community, but we just did a visual observation on this. We didn't have to do any testing, just some visual observation and a little bit of research into the state GIS database. As you can see, Basin 1 flows into Basin 2, which is near their clubhouse. Basin 2 just discharges to the floodplain to a nearby river. Oops, sorry. So here is Basin 1. And the red line you see here was the area or the level to which the water was rising in the basin. You can see that it is rising above where the fence level is at the end of that basin. It was coming up into the rear yards, up to the decks and the foundations. So as you can imagine, that's a little would make anyone very nervous. So we had to figure out why the water was rising so high in this basin for storms that shouldn't cause the water to rise this high. So when we looked in this basin, we could see that the low flow channels had some silt in them. When we looked in the outlet structure, there was some silt in there. Then we went over to Basin 2 and we evaluated Basin 2. And just to refresh your memory, Basin 2 is the basin that's getting the discharge from Basin 1 where they were having the problem. So now we're looking into Basin 2, and Basin 2 was loaded with silt. And here's the outlet structure. I tried to get put a panoramic image here for you, but I have used two pictures. So on the west side was a very large outlet structure. On the east side, you can see that the basin is enclosed by an embankment and a segmental block wall. And you can't see it in this picture, but all of the roof drainage was also discharging into this basin from the clubhouse and the nearby buildings. So when we took a close look at this basin, everything was silted in. It was loaded. As you could see this outlet structure here, you could see the leaves. You can't even see the low flow channel here. There's actually a low flow channel that comes from the inflow head walls to this outlet structure through this grate. It was loaded with silt. What you see here in the bottom right-hand corner is the inside. When we peered into the outlet structure box, it was filled with silt above the inflow pipe. I don't think I have pictures here of what's under this inflow grate, but it was pretty loaded with silt. So just to give you the end story of this, the recommendation was for us to not do anything, but in terms of any kind of improvements or specs, but to first come and clear all of this out and get rid of all the silt, clean up the basins, get rid of the leaf debris, the trash debris, the silt. And if it still wasn't functioning properly, that we could come in and take a second look. But with the cleanup and the maintenance, everything started functioning properly again, and the issue resolved. So just in general, maintenance is very, very important, especially for stormwater basins. As you can see, systems that are not maintained can cause some damage, can cause property damage if they're not maintained properly. Also, even if they're not causing property damage, whenever you let a maintenance issue go, over time, it becomes more expensive to fix. So it's better to do preventive maintenance as you go along so that you don't develop a problem in the first place. And if you do have to do corrective maintenance, it's better to perform corrective maintenance sooner than later. So a lot of the newer communities are required in the state of New Jersey to have stormwater operations and maintenance manual prepared as part of the design process. So that may be a separate document that you have, or it might be in your governing documents. If it's not, there are state guidelines for maintaining stormwater basins. So again, if you live in a community, you're managing a community, you're a resident of a community, and who's responsible for coordinating maintenance, what you want to do is after a large storm, and the state says any storm of 1 inch rainfall or greater, unless you're standing around with a rain gauge, it's hard to know. But really, any storm of any significance, you want to go out there and take a look at your system. Is there any damage? Is there any siltation? Is there any debris accumulation because of the amount of water flowing through trash racks or stormwater grates? Also, leaf fall at the end of the year that gets into stormwater systems. Many times when I go to look out to a site to look at a drainage deficiency, the first thing I do is I look in the catch basins to see how much accumulated debris is in there. And a lot of times they haven't been cleaned out in years. So again, very important to clean everything out after storms and get rid of all that debris. You want to inspect your structures. Are they deteriorating in any way? Is there cracking? Is there erosion around those structures? Are they beginning to? A lot of these structures are made of concrete and have rebar in them. And once they crack, the water gets into the structure, reaches the steel. That steel oxidizes, begins to expand, and destroy the concrete around it. You want to inspect any structures, again, that trap debris. You may have trash racks on your outlet structures after a big storm. they can often have quite a bit of debris in there. You want to have your maintenance company clean that out. So it's very important. You want to inspect swales anywhere concentrated flow happens over the surface of the ground. Inspect it for erosion. One of the items of maintenance that I often see that have been let go for a long time is, I mentioned the conduit outlet protection before, where the water comes out of a flared end section or a head wall into where there's an outflow point. That outlet protection, often in the form of riprap or a concrete apron, that needs attention too. I see a lot of communities where the outlet, because of a large storm, that the riprap has actually been displaced and pushed out of the apron, and it hasn't been repaired. And every time there's another storm and that water comes through there, it's digging deeper and deeper into that soil. So you want to look after the storm too, to make sure that your conduit outlet protection is in place, it's doing its job, and it's protecting the soil below the outfall point. And that concludes my presentation. So we can do some question and answer if you'd like. If anybody wants to present a question, we can discuss it here before we close for the day. I have a question. I have a question here. What is the acceptable length of time for water to sit on paved surfaces? Again, you want to, there are two conditions here, and I'm glad you mentioned specifically a paved surface. So there are two things that can happen. As we remember, our drain time criteria for an open area is 24 hours. So after the rain event, you want to look at the paved surface. You want to look for any ponding or bird baths, things of that nature. And if you see that, you want to take care of that, because clearly during the winter months that can freeze. That could be a problem. There are conditions, however, where and I see this a lot in sloped communities, that a lot of times the soil remains saturated for a longer time than water sits on the pavement surface. So you can have water that's flowing out from behind that curb, either through the curb joint, a concrete curb, or with Belgian block curb. It comes right through the joints in those curbs, and it will continue to flow on the pavement surface long after that 24-hour period, especially during periods of high groundwater. So not to complicate the matter, but that is a possibility as well. So that pavement is doing its job, and that it's moving the water because it's coming out from behind the curb. But anytime you have a bird bath or a ponded area or standing water on a pavement surface, you want to have that evaluated, because water does a lot of damage to asphalt.
You didn't answer my question.
What was your question?
How long, what is the standard? It seems to me in past webinars, there was like a standard, like the 24 hours for the open areas, et cetera. There was a 24 or 48-hour period that it was acceptable for water to sit on paved areas after a storm.
There, I put it up there. Yes, it's not that it's acceptable for it to sit there, but you want to see full drainage within 24 hours.
Okay,
Even if the
so this
pavement
doesn't
is still
address paved areas, like walkways, like sidewalks, for example.
the same thing. The same thing would apply. You want that water to be completely gone within 24 hours,
Okay.
but you may have a seepage condition from the nearby soil that will keep water flow. I just had a project just like this, where it was like a river on their sidewalk, like 2 days, 3 days after it rained, that was causing erosion along the sidewalk. It was digging up the soil. So there was still water there, not because the pavement, there was something wrong with the pavement, but because there was a seepage condition. So you want to, even though we can't get rid of that seepage condition, we can manage it. So I guess in general, if you have pavement that has water that's standing on it 24 hours or more after the end of a rain event, you should have it evaluated.
Thank you.
Okay, I have a question here. What can be done to minimize mulch runoff that clogs a street drain and floods the street? You might want to, again, this is sight unseen, but I see this a lot. You might want to consider doing away with the mulch. There might be a landscaping alternative. I often see in areas where mulch can impact the stormwater system, they'll get rid of the mulch and they'll do a river stone. That again, you're getting into the aesthetics and everything. I don't really deal in aesthetics that much, but for landscaping, but that is an alternative. Is you can get rid of the mulch. You can put down a landscaping fabric and a river stone over it to keep that mulch from running off. I mean, short of that, you'd really have to just constantly clean that drain. There's really no way around that. Okay, I have another question. How do we correct an issue where there's definitely some type of high water table under the property that is causing deterioration of asphalt and concrete, settling, erosion, gator cracking, holes in the asphalt? So again, sight unseen. I'm just gonna go on just some past projects that I've done. So we want to look at the reason why there is water under the pavement. So if it is a high water table, the solution is always not always, but oftentimes to create a void where that water can go, a subsurface void. So oftentimes a perforated pipe can be used to create that void, so that the water that's coming up, that always wants to be there, is going to go into that perforated pipe and be carried off. There are other ways to manage it where that is not a possibility, and you need to stabilize the soil. Oftentimes I see pavement projects where there's this really squishy clay soil, not because the groundwater is high, but because the clay just wants to hold a lot of water. So where that condition is really bad and causing very rapid accelerated deterioration of the asphalt, what we'll typically recommend is that that area be excavated. And if you can't get down to a suitable soil, we'll put down a geotextile fabric, which it doesn't replace the soil, but it gives the soil more of a stability, so you don't have, it's not quote unquote squishy. So they'll put down the fabric, they'll backfill with a very structural material like a DGA. It doesn't get rid of the clay soil. You can't get rid of your clay soil, but you can create a layer that is very stable, that will mitigate some of that. So there's a number of ways that we can deal with squishy soil and high water tables. Again, as I mentioned in my presentation, there's different sources, different solutions, but those are the types of remedies that I have seen and dealt with. All right. Thank you very much, everyone, for attending. And again, if you are here for CEU credits, please contact Jen and Chelsea. Their email is right in the chat. Have a great day, everyone.